Hello, everyone. Welcome back to another exciting session on automotive cybersecurity mechanisms. In our previous videos, we explored some of the cybersecurity mechanisms and the layered automotive approach to the automotive security. This approach was designed basically to protect the ECU, which is essentially the heart of the vehicle. Today, we'll deep will delve a bit deeper into to understand one more critical cybersecurity mechanism, which is secure boot. So, what exactly is secure boot? As vehicles become more connected and reliant on sophisticated software, ensuring the security of our systems become more important than ever. Secure boot is one of the foundational technologies that help to protect our cars from cyber threats. Let us explore what it is and how does it work. Secure boot is a security standard that is designed to ensure the device boots only the software that is trusted by the manufacturers. In the context of automotive systems, this means that each electronic control unit in our vehicle starts up with a verified software, preventing the malicious code taking control. As we know that modern vehicles are incredibly complex, with numerous ECUs controlling critical functions such as braking and steering systems. Without proper security measures, these systems are vulnerable to cyber attacks. Imagine a scenario where the hacker takes control of your braking system and accesses all your personal data. Secure boot mitigates this risk by ensuring only verified and unaltered software can run on your vehicle's ECU, protecting both your security and privacy. So now I would like to ask Dharmesh to further elaborate a bit about how this secure boot process takes place.
So thank you, Riva, for explaining a brief about the secure boot. So before we dive deep into the secure boot part, uh, there are some keywords which is used in secure boot, which we need to understand a bit, and then we can move on to the deep dive into secure boot how it works. So first is bootloader or boot manager. So bootloader is a software component used to initiate the boot up process to the issue main software, including copying the software into the RAM and perform any checks on the software before boots up. Another is digital signature or CMake. Why I mentioned or here that will come in coming slide come to know. Digital signature is a mathematical technique used to validate the authenticity and integrity of the software, which we already seen how it works in our previous part of this session. Uh, Next is MAC here. So what is MAC? So MAC is message authentication code, also refers to a tag, is used again to authentic the original nature of the message. Next is verification process. So verification process verifies the flashed firmware whether it is authentic or not, or somebody have tampered with the existing software or not. And last important word is root of trust. So root of trust is a foundation on which all the security related operations uh, of a computing system depends on. It contains the key used for cryptographic function and enables a secure word process. So its inherent trusted means that we by design itself it should be trusted, and we trust that whatever whether it's software relevant then some kind of code or hardware mechanism. So now let's see in deep dive into secure boot. So there are two ways we can verify the software image. Method one is symmetric algorithm, which consists of message authentication code. Uh, Popular is CMake and HMake. Uh, so this is method one, and method two is asymmetric algorithm, which is also known as public key cryptography. So the popular public key cryptographies are RSA and ECDSA, which stands for Electrical Cloud Digital Signature Algorithm. I mentioned above or between the digital signature and the MAC algorithm, because there are two methods through which we can perform the secure boot: symmetric algorithm and asymmetric. Let's a little bit see how this works. So here in the image left side, you can see the symmetric algorithm, which solely depend on the MAC verification. So when issue boots up, root of trust code will be executed, and this will then verify the stored bootloader MAC, which is stored during the flashing time, and again running up the software, it will calculate this MAC and compare it. If both are correct, then it will say okay. This goes till the application software. So again, for each block, the MAC will be calculated and compared. So this approach is using one key, which is private key. That's why it's a symmetric, and using the MAC. So MAC is again algorithm, two types, CMAC or HMAC. So cipher based or hash based algorithm. So that's why this part of the booting, we call as secure booting, is symmetric algorithm, secure booting. The other way is asymmetric algorithm. So using the asymmetric algorithm, we already know asymmetric means there should be two keys, private key and public key. So here the validation will happen through the public key on this digital signature. So on our last lecture, we seen that how the software will be signed and flashed in the software. So signed software will use the private key of the manufacturer, and on the issue to validate this signature, we are using the public key of the issue. So here same process, root of trust code will then first verify the bootloader using the public key. It will just decrypt it and check the value whether it is correct or not. So if root of trust will first verify the bootloader using the public key, it will decrypt the signature, it will compare. If both matches, then yeah, so bootloader is okay, and it will move forward to the next step of the software. It will go till the application, complete application. It will verify all the signatures, and then it will switch to the new software, or finally boot will complete. Now in this figure, this is the general overview how boot process will work. However, this will be implemented in different projects in different way, because there will be different timing requirements for each of the project. But to give an overview how this will work, so that's why this example I have taken here. uh, we can see in the example, I have two cores. One is HSM core, which is the trusted entity for me, which will hold all the cryptographic keys, perform the acceleration operations to calculate or compute these hash values, etc. And I have the host core, where my bootloader or boot manager will run and verify or perform the calculation. So the first step, HSM starts up, and which is for me it's root of trust. It will verify the host boot manager, uh, whichever the algorithm we are using, symmetric or asymmetric. It will verify whether this part of the code is uh, valid or not. Then it will move to the host boot manager, where part of the software block it will take. It will check whether the signature for this is matching with the stored signature, which is again in the HSM core. During the flashing, all these block signatures will be stored here. It will compare. If both will be okay, then it will say okay, it will move to the next block. So here the iterative process I see show here, because there will be a huge software. There we are splitting the software into different blocks, and until the last block is completed, then we'll arrive okay whether the whole software is authentic, means nobody tampered, every signature verification or hash value verification is passed. Then what action needs to be performed. If any of the steps fail in between, then how to react on that. That we will check in the last slide of this presentation. If something fails, then what are the possible things you can do? So this is the general process, how it works. Uh, in next slide, I'll just explain about two ways. It's depend, as I mentioned, depend on the project or depend on the architecture, how this mechanism will be implemented. Uh, so first approach is monolithical approach, where after the reset, the initial program loader will be verified, and then the entire software itself stored in the NVM image will be verified. So this one approach will work if there is no timing restriction, or let's say you will have enough boot up time uh, in your software. Next is the staged secure boot approach. This is more commonly used, where uh, you don't wait until the entire software is validated, but you just initially, once verified, then block up the software. You will start booting up. If it's okay, then perform some action, then go to the next block, uh, verify it whether it's successful or not. So this process will go until the last block you verified. If something fails, then again what action you need to take, that will be explained in the next slide. So what happens if one of the stages fails to verify? So if one of the stages fail to verify, then one option is system reset. You reset the system again. Second option is execute the next stage with reduce the privilege. So one example is like disallowing the usage of the cryptographic keys, which is for the next step, let's say performing some operations using this key. So that privilege will be restricted, or certain peripherals which will be not initialized. The third point here is execute an alternate verified application. This is mainly seen in the OTA. So when we see there are many applications or different application or different versions, if something fails, then roll back or previous version, execute the previous version and discard the newer version. The last one is staying in the current boot stage, to do not perform any action and stay in the current boot step. So this is the overview about the secure boot, how it works, and yeah, we are open for any questions anybody has on this topic.
Mhm. Can you go to one of slides before where there was HSM core?
Mhm.
Okay, maybe a question on this. For this secure boot, do we always need an HSM, either integrated in the hardware or an external HSM? Is it mandatory?
So answer to your question, uh, it is not mandatory, but some kind of root of trust to ensure that uh, some kind of hardware separation or secure code where you are trusted that nobody is tampered this. So that mechanism should be there to at least the startup and verify your bootloader. But it is mandatory for the secure boot to have HSM. I would say no. It's depend on the implementer. If they have available resources, they have hardware, then they can use HSM. Else, same thing they can implement in software also, or using the existing hardware also. So yeah, that's my answer. If anyone want to add on something on this.
So the main use of HSM is to reduce the complexity from the software part. So maybe I can implement whatever required cryptographic algorithm in the software also maybe, but it may use so much of core for the CPU usage and memory and so on. So that's what like we are using HSM, then it may do some cryptographic algorithms in the hardware. So as Dharmesh mentioned, like it depends on the project, maybe if my ECU is having large software and if I want to implement the secure boot only with the software support, then yeah, the starting time would be too large, or the software cannot handle all the complexity. So then the HSM is good option to use. Otherwise, maybe in some small issues without HSM also we can implement these features. One more question from my side. So we seen previously about CMake and HMake. So these are two different approaches which can be used for the symmetric algorithm. So could you give some more details about this? What are the difference in the CMake and HMake?
Mhm. Okay, so CMAC, how it is calculated is it requires the secret key, uh, and using this key along with the message, you will calculate some kind of message, means some kind of encrypted value, and that will be appended to the message. So this is cipher based message authentication code. So this will be validated in other side when you send using this CMAC. On other hand, you have the HMAC, which is the hash based message authentication code, where we use the hash function to calculate this MAC. So let's say we have the message, and first you will pass this message through hash function, and you will arrive fixed bit of length using this hash function. Let's use the SHA 256. Then 256 bits of value I will get from the message as output. Along with this hash value, again one more time you will hash this value, and once this hash value is one more time derived, then that padding will be added to the original message, and this will be then other side it will be checked. So that is the two way we can calculate, so using the CMAC or HMAC.
So, since we spoke about algorithm, so can anyone say like what factors should be considered while choosing the key algorithm?
Uh, okay. So maybe if I can answer that. So as per my understanding, mainly here we are talking about symmetric and asymmetric algorithm. The main difference here are in the symmetric algorithm, we just have one key, which is private key for encryption or decryption. And in the asymmetric, there are two different keys. One is private, who is encrypting the data, and the public key is for who is decrypting the data. So the challenges with the symmetric algorithm would be like the same key is there for both the end of who is decrypting or encrypting. So then we also have to think about how these keys will be provided or transmitted to the ECU. And so someone is like generating the software, they also have the same key, and in the ECU also the same key is there, and which are used to perform this complete symmetric algorithm based secure boot. So here there could be some challenges regarding these keys. While in the asymmetric, both keys are different. So private key is not shared with anyone. So that is only known to the uh, one party, while the public key is public. So it can be shared with anyone. And I think that is easier to distribute. So it can be distributed. And if anyone knows the public key also, that's fine, I think. So that is my opinion.
So just to add on, I think also what it matters is I mean, Dharmesh did mention about the different algorithms in even in the symmetric and asymmetric, right? So he talked about the RSA, he talked about the ECDSA, etc. So there are various algorithms, and there'll be multi-layer encryption. So it all depends on what kind of let's say mechanism do you want to use, what kind of protection, what layer of protection you would want to use, and it also depends on how much time it is required for you to decrypt. Encrypting it's okay because you are going to encrypt outside and send it. So in the decryption part, when you're doing the secure boot, startup time would probably increase. So all these factors also needs to be considered, and this is a very good point which normally or typically the architects will consider while designing the cybersecurity concept for either the system or the software part. If it is hardware based encryption, then probably at the system level itself, which also will take over at the software and the hardware level. But if it is just a software based, then you will also look into detail in the software architecture to consider all the factors.
Yeah, additionally, one more thing. So, if we think about the timing perspective, then always symmetric algorithm calculation would be much faster than the asymmetric one. So that again, like requirement, how faster you want to make boot process. So if that is very critical deadline, then yeah, choosing symmetric would be better. But if you think about more security perspective, then asymmetric would provide more security than the symmetric algorithm.
So, one question I have, we talked a bit about root of trust. So, what is root of trust in HSM core, and how do you ensure that the HSM is not compromised?
Okay, that's a good question. So answering your question, the root of trust, how HSM will be ensured. The HSM itself or the root of trust means that okay, we are trusting that, and whatever the code or action it has to perform, that will be by design, it will be secured. So HSM will have either memory segment or some memory protection where it is uh, nobody can tamper it or very hard to tamper this particular code, then this will consider as root of trust.
Right. However, to answer the second part of the question, uh, if HSM itself can be compromised, right? So this is definitely a possibility. Of course, whatever uh, protection you would build, you will always have a way to break it or a mechanism to break it. So this is where that's how we all started this discussion, right? You have layered architecture. So normally what happens is if let's say your HSM is compromised, so there will be initial handshaking messages. That means your HSM and your host core, they will always exchange initial messages. And with that initial exchange of messages, you would know whether your core is compromised or HSM is compromised. So that would establish, let's say, the root of the chain of trust, right? So to add multi-layer protection here, you can always add different layers. That means it's not just one layer of security. That means it's not just one message where you can see that, okay, I exchanged this message, I am expecting such a message, and I got that message, which means my HSM and the host core is secure. No, you can always have multi-layer. That means first layer would be the root trust, then you will have an intermediate let's say key which will be derived from the root key, then you would have maybe a dummy key. I'm just telling you there can be multi layers, right? So having all these things, it would help you to recognize whether certain hardware, the HSM or the core itself, is compromised. Now, apart from that, one other thing that you can also do to ensure that your HSM is not compromised is your HSM and your host core will always talk. right? There would be some channel. It can be through SPI, it can be through UART, it can be anything. It depends on how your hardware architecture is, how would you would have connected. So there will be sessions, right? So try to have unique key for every session. That means even if certain keys are compromised in one session, the next session when it gets opened, you have a unique key, you have a unique handshake, which means the attacker will have to redo the whole process again, or should always keep the point in mind that the session should always be kept open. Apart from that, you can also add one more saying that if the session duration is longer than certain amount of time, then automatically close the connection and reopen the connection, or maybe exchange some security messages. So these are some of the extra security measures that you can adapt, or you can implement. Now all these things, as part of the architecture, it will come into picture. Now whichever is the most secure part of your, let's say, the ECU or of your complete system, you would want to incorporate all these things here, right? So you wouldn't, these are costly operations. You wouldn't want to do it for every ECU. You would have to decide where should I put all these mechanisms, and based on that you would decide what layer or how much layer you would want to put in the security.
Okay, maybe a question on the process part. Let's imagine if it has been decided that secure boot has to be, included in the software development, which is like in most of the projects, which is the case. Of course, it differs which HSM you use or which algorithm you use. These decisions will differ. From a cybersecurity engineer's perspective, who is deriving the requirement, what are the important factors to consider and what kind of a requirements related to the secure boot has to be captured?
Uh, yeah. Uh, Answer to your question. One I could think about is how much time the boot process will take. So there should be a requirement related to boot timings, and then you will choose okay how you want to proceed with whether it's a monolithic or stage wise the secure boot. So one thing I would say engineers should keep in mind while deriving the requirements.
And also the same thing, I think what Pran
Also,
mentioned, like some there are some variables like what kind of algorithms are used, how it should be implemented, like it is only software based approach or the HSM is used and like that. So maybe all these things also has to be clarified and derived as a requirements.
So I have a question related to security and threat. So how does this HSM protect against common attacks targeting the secure boot process in vehicles?
So that's a good question. So to answer this question, so let's deep dive a bit on what are the common attacks, right? So when you're talking about common attacks, I mean right now the state of the art uh, used technique in Tara is tried right now, right? Spoofing, tampering, denial of service attack, intrusion detection, elevation of privileges, right? Uh, Non-repudiation, etc. Normally, what would happen is when you are trying to the secure boot itself, you are trying to secure the whole ECU from cyber attacks during the boot up time, right? Or if you are sending a unauthenticated software, right? So during boot up time, you can probably try and detect that. So one thing that can happen is denial of service attack during the boot up time itself. If somebody tries to overload the system, that is something that can happen. Then some keys can be extracted during the boot up itself, because during the boot up time you can probably read out some of the memories, because once you have authenticated the session, so between the uh, HSM and the core itself and the ECU. Once the authentication has happened, then you have a secure communication that is established. With that secure communication, you can also try to extract some of the keys. And once you extract the keys, the possibility of attacks are a lot. So this is where when you're using things like HSM, you have multi-layer encryptions or you have session-wise encryptions. This will enable you to protect even if certain keys are compromised. It will help you protect the overall communication. The other thing is you use HSM to store the keys. So where you store the keys also becomes important, right? So HSM, you don't store the keys just like that. You would probably encrypt the key itself and store it, right? So the whole key, whatever you use it for the encryption or decryption, it itself will be a derived key, or the primary key will be encrypted and used as a derived key for the further operations. So all these things can be also stored in HSM itself, which is because HSM is considered to be the root of trust, which means there in probably a secure memory, an encrypted memory, you would store all these keys, thereby making sure that you provide one more layer of security and make it hard for the attackers to get access to these things.
So thank you so much guys for watching our video. If you found this video informative, you do subscribe and share it with your fellow colleagues and friends, and stay connected for further more updates on different cybersecurity, automotive cybersecurity topics. Thank you.